Today we are talking about 3.2 notes. This will cover sections 2.1 to 2.2 in our textbook if you're following along with the textbook. Today's section is about absolute value equations and inequalities in one variable. Let's start off with a basic understanding of the absolute value. So if the absolute value of x equals 6, then x equals 6, but x could also equal negative 6, because remember, the absolute value of 6 is 6, but the absolute value of negative 6 is also 6. Why is that? That's because absolute value means the distance from 0. So both positive 6 and negative 6 have a distance of 6 away from 0. All right, let's use that knowledge we just reviewed about the concept of the absolute value function, and let's use that to help us solve an absolute value equation. So we have the absolute value of x minus 2 equals 5. Now, using what we just reviewed, that means that it could be positive 5 because the absolute value of positive 5 is 5, but it could also be the absolute value of negative 5 equals positive 5. So that inside could equal positive 5, but it could also equal negative 5. So what we're going to do is we're going to set the inside equal to positive 5, and we're also going to set it equal to negative 5. Now, these are both x minus 2 equations, so we can solve them simultaneously. And that means we are going to add 2 to both sides, and we get x equals 7, and on the right we get x equals negative 3. Now, here's the thing. You want to check for extraneous solutions. An extraneous solution is, it may work in the equation once we took it out of the absolute value bars, but when we plug it back in, it might not make the absolute value equation true. So, and again, you don't have to show us the check step, but we do want you to complete the check step, even if it's inside your head, because there's not going to be a lot of partial credit on this, because you can go back and check your work. So we check, we have 7 minus 2 equals 5. Well, absolute value of 7 minus 2 is the absolute value of 5, and the absolute value of 5 definitely equals 5. So he works. Let's try the next one. The absolute value of negative 3 minus 2 equals 5. Well, negative 3 minus 2 is negative 5, and that equals positive 5, so that works as well. So since it works in both equations, we can say that both solutions are solutions to the absolute value equation. So when we go to write that, we use what we call solution set notation. Solution set notation. It's always in the birdie braces, and it's always the small answer, comma, the large answer. So the proper format is always small, comma, large. So in this case, negative 3 was smaller, and it worked. So x is going to equal the solution set of negative 3 and 7. And this is how we want you to write your solutions, is in solution set notation. Let's look at solving some more absolute value equations. So our example 2 says that we have negative 2 times the absolute value of negative 3x plus 3, and that equals negative 12. Now, we want to isolate the absolute value. So nothing can be going on outside of the absolute value when you go to set it equal to the positive and negative values. So it has to be completely beside itself. That means you may have to undo addition or subtraction, you may have to undo multiplication, something like that. But you want to isolate the absolute value by dividing by the value in front of the absolute value bars. Never, ever, ever, never distribute across the absolute value bars. And the way I always tell my kids to think about it is think about the absolute value bars kind of like an electrified fence. You never want to jump over an electrified fence because chances are you'll be a crispy critter, and we don't want that to happen, okay? So no jumping over electrified fences, which is what the absolute value bars are. So what we're going to do is we are going to divide by -2. Now notice when I divide by the -2, I don't actually touch what's inside the absolute value bars because that's an electrified fence, and I'm pretty sure with my luck I would land on the fence and be a crispy critter, so we don't want to do it. Don't touch anything inside the absolute value bars. So that leaves me with the absolute value of -3x plus 3 equals 6. Now remember, that inside can be +6, but it can also be -6 because the absolute value of -6 is 6. So we're going to set that equal to +6 and -6. Now, the left sides are the same, so we can solve them simultaneously. I'm going to subtract by 3 on both sides. And that gives me, oops, I apologize, I did not finish that out. So that gives me -3x equals +3, and -3x equals -9. Now to continue solving, we divide by a negative. And that leaves me with x equals -1 or x equals +3. Now, we need to check for extraneous solutions. That means when we take them out of the absolute value bars, it could work, but when we go back and plug it into the real problem, it doesn't work out. So let's try -1 first. So I have -2 times the absolute value of -3 times -1 plus 3 equals -12. Well, -3 times -1 is +3. 3 plus 3 is 6. The absolute value of 6 is 6. So is that a true statement? Does -2 times 6 equal -12? It does. So now let's go and we're going to try the +3. So I have -2 times the absolute value of -3 times 3 plus 3, and we're going to see if that equals -12. Well, that's -9 plus 3. Absolute value, so that becomes what? -6. Absolute value of -6 is +6. And that also makes a true statement. So we can say, our solution is -1 and 3. All right, so what I want you to do now is I want you to pause the video and I want you to try to work out example 3. So work it out, and then when you're done, hit play again and we'll talk our way through it. Okay, let's see how you did. So the first thing is, again, can't distribute across the absolute value bars. We don't want to be crispy critters. So we are going to divide by -5, and that gets me the absolute value of 4x minus 5 equals 15. Well, we know that can be +15 or -15. So I add 5 to both sides. So that gets me 4x equals 20, or 4x equals -10. I divide by 4, and I get 5, or -5/2. So I have to plug it back in, and they both work. Now guys, I know you think, well, aren't they all going to work? And that's not the case. That's not always the case. You could have just one solution that works, both solutions could work, or neither solution that could work. So You want to make sure that you check them because that way you don't end up getting something wrong because you failed to check your work. All right, so that is how we do example 3. So let's look at this one. We have 3 times the absolute value of negative 3x plus 3, and that equals 6x minus 12. Okay, so remember, the first thing we want to do is we want to isolate that absolute value. Remember, we cannot distribute that 3 across the absolute value bars because that's like an electrified fence keeping us out. So we can't distribute that 3. He can't jump over that electrified fence. So we have to divide every part by 3. Okay, now notice on the right, I divided both terms of the expression by 3 instead of doing one big zoom, division bar in 3. You don't want to do that because more than likely you might make a mistake. So if you have an expression on the right side, divide each term. It keeps things a little bit clearer. So that gets me negative 3x plus 3 equals 2x minus 4. Okay, so remember, according to our last example, it can equal the outside or it can equal the negative of the outside. That rule still applies. So that's why you'll see that I set it equal to 2x minus 4 and I set it equal to the negative of 2x minus 4. So we're going to start on the left side and we're going to solve that. So I'm going to get the x's on the same side and the constants on the same side. So I'm going to subtract 2x from each side and then I'm going to subtract 3 from each side. When I do that, I get negative 5x equals negative 7. I then divide by negative 5 and I get 7/5. Now, on the right side, I'm going to have to distribute that negative 3 to that negative sign. So on the right, I'm going to have to distribute that negative sign to both terms inside the parentheses. So that way I get negative 2x plus 4. Now, on this example, I'm going to add 2x to both sides and subtract 3 from both sides. So that way I end up with x equals negative 1. So I want to check for extraneous solutions because right now I have negative 1 and 7/5. So let's check negative 1 first. If I plug negative 1 all the way back up there into that very first equation, I get 18 equals negative 18. Now, that is never, ever, ever going to be true. 18 will never equal negative 18. So that doesn't work. Now let's try 7/5. Well, when I do all the work and I plug 7/5 in, I get 18 over 5 equals negative 18 over 5. Again, never, ever, ever going to happen. So in this case, even though we got 2 solutions that worked when we took them out of the absolute value bars, when we plugged them back into the original equation, it didn't work. Now, one thing I do want to point out to you also, little side example here. What happens if I were to give you something like negative 2x plus 4 equals negative 7? And it's just by itself, I'm not dividing, this is the problem. What if I gave you 2x minus 4 equals negative 7? Would that be possible? The answer is no, because an absolute value will never, ever, 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 ever equal a negative number on the outside. Now, you saw in one of the previous ones, we had negative 2 times the absolute value equaled negative 12. If you have a negative on the outside that you're going to have to divide by, it is possible for that right side to be negative. However, if, like in the example I just wrote, the absolute value equals a negative and there's nothing on the outside to multiply or add or subtract, this could never equal either. So here that would be no solution as well. So if you have an absolute value and that's all it is and it equals a negative, you're going to say no solution because it's not possible. Now, let's talk about an absolute value inequality. So up to this point, we've just been talking equations. So now let's talk about inequalities. So if we have less than or equal to, that's less than. Well, if you think, that kind of sounds like less than. That was presented to us by a kiddo a few years ago. They're like, well, when I think of less than or equal to, I think less than. And that means it's an and inequality. It's going to be turned into a compound inequality. So your answer, your graph, your solution is going to be an intersection. So for example, one part will give you that it goes with the green arrow. It goes to the left. And then the other part would say, well, it has to be greater than or equal to. So when we're talking your graph, it would be the intersection of these two parts. So this wouldn't even be part of it. So your graph would be open circles or closed circles, depending on the sign, and it would be the shading in between. So you might have something and you might end up with a compound inequality that looks like that. So the other way I help to remember when I'm thinking about graphing this is you can think of, well, it's the overlap, but there, X is in the middle, and so you're only going to shade between 2 and 5. Okay? So that's what you're going to do there. Now, for greater than or equal to, we're going to think great or. So that's going to be an opposite. So you might have something that says, hey, X is less than -1 or X is greater than 3. So, and I guess in this case, they would be or equals to because we use closed circles. So that's what your shading would be like. Okay, so remember, for less than or greater than, we use open circles. For less than or equal to or greater than or equal to, we use closed circles. So this is something that would be represented by a great or. Now you're probably thinking, well, how does this relate to the example? So glad you asked. Let's look at a few. Okay, let's look at how that actually applies to a real absolute value inequality. So we have the absolute value of -2x plus 7 plus 5 is equal to 14. So the first step is always, I have to isolate the absolute value. So I'm going to do that by subtracting 5. So that gets me the absolute value of -2x plus 7 is greater than or equal to 9. Okay, well guys, that's greater than or equal to. So greater, it's going to be an or inequality. So great or. So that means it's going to be the opposite or the union. Now this is where you really want to pay attention. This is how I break it into two inequalities. For the first inequality, I'm going to drop, I'm going to drop the absolute value bars, and that's all you do. For the second inequality, you're going to drop the absolute value bars, flip the symbol, and change the sign. So, for the left inequality, drop the absolute value bars, solve. For the right inequality, you're going to drop the bars, flip the symbol, and change the sign. So for an or, that second inequality is drop, flip, change. Then you just solve it like normal. We have to undo addition by 7. So I'm going to subtract 7 from both sides. And this is really cool because I can solve them simultaneously. Now the other thing I want to point out is you've actually got to write the word or. Or is part of your answer. You have to write it. Okay? So that gives me -2x is greater than or equal to 2, or -2x is less than or equal to -16. So now we divide by -2. But wait, what happens when I divide or multiply an inequality by a negative? That's right, you have to flip the symbols. So here I get x is now less than or equal to -1, or x is greater than or equal to 8. So now when we graph, I always put 0 in the middle, and then I just plot the end numbers. So 0 and -1, and then 0 and 8. Now remember, if it's less than or equal to or greater than or equal to, you're going to use a closed circle. If it's strictly less than and strictly greater than, you're going to use an open circle. So or equal to gets a closed, just plain less than or greater than gets an open. So I have x is less than or equal to -1 and x is greater than or equal to 8. So if you remember, it's an or inequality, so that means we plot the endpoints and we shade off in the opposite direction. What this means, if you look at it graphically, is that the point -1 and everything to the left would make my inequality true. But I could also say 8 and anything to the right would make it true. So that's really what your shading represents. Now, the graph is not your whole solution. What I boxed in red, that's what we want to see for your solution. You have to write the compound inequality, which in this case is an OR compound. You have to write the inequality as well as do the graph. Okay, so you have to do both. Let's look at the left inequality now. So this is the absolute value of 2x minus 5 is less than -7. This is less than, so you want to think and. Less than and. Okay, so here's what we're going to do. Whenever you have a less than or less than or equal to, you're always going to put that value between +7 and -7. The negative will go on the left and the positive will go on the right. So when it's a less than or equal to, what you do is you take the inside and you squeeze it between negative and positive value of that number outside or the expression outside. So you always squeeze the inside between the negative and the positive of that right-hand side. And then we just solve it like we would equation, except for in this case, what we do to the inside, we have to do to both of the outsides. So this is less than, I squeezed it between -7 and +7, and then I'm just going to solve it. I'm going to add 5 to every side. So 5 to the inside, 5 to the outsides. And that gets -2 is less than 2x is less than 12. Then I just divide by 2. So that gets me -1 is less than x is less than 6. So we do our number line. I plot, now instead of 2, you could have plotted 0. Doesn't matter. Typically what I do and what you're going to see on the answer key is that I plot 0 and then the 2 numbers. Now the only caveat to that is if 0 is not in between the 2 numbers, you'd probably want to pick a number that is to be kind of a center point. But in this case, I've got a negative and a positive. So I used 2, but I could have used 0 as well. So this case, we're going to have open circles. So I'm going to have an open circle at -1 and an open circle at 6. And because x is in the middle, I shade in between. Now, the question is going to come up, do I have to put this shading on the number line or can I do it above? Okay, guys, this is what I'm going to tell you. It doesn't matter. So you could easily do it like this. And then you'd have open circle, shade in between. So that is perfectly fine to do it that way too. If you don't want to do it on the number line, you can do it above. All right, so what I want you to do now is hit pause, and I want you to try the second inequality. Okay, let's see what we did here. This is a greater than or equal to, so great or means it's going to be an or. So for the first inequality, since it's or, I drop the absolute value bars and just write it. For the second inequality, you drop, flip, change. Drop, flip, change. And then that gives me 1/3 x is greater than or equal to 7, or 1/3 x is less than or equal to -3. To undo multiplication by 1/3, I'm going to multiply by 3, and I get x is greater than or equal to 21, or x is less than or equal to -9. Then I plot it. There you go, and since it's an or. So remember, this has to be your whole solution. You can't just do the graph. You also can't get away with just doing the inequalities and not the graph. They come as a combo pair. You don't get one without the other. All right, let's look at this one. This one's a little bit tricky, which is why it is included as an example. So we know the rule is that we have to isolate the absolute value. So I'm going to divide by -3 on both sides. Now when I do, remember that does two things. When I divide by -3, it flips it from less than to greater than because it flipped a symbol. But now I have x minus 5, the absolute value of that, is greater than or equal to -11. So it's no longer an and because it was less than, so and. It's now become an or because I divided by a negative. So I'm going to set up my two inequalities. So first inequality is you drop the absolute value bars. And the second one is you drop, flip the symbol, change the sign. So since it's or, we're going to drop, flip, change. So that gives me x minus 5 is less than or equal to now positive 11. So we add 5 to both sides, and I end up with x is greater than or equal to -6, or x is less than or equal to 16. And you're like, well, okay. But check it out, guys. When we graph it, there's x is greater than or equal to -6. Here is x is less than or equal to 16. So do you see how they overlap? So since the red starts at -6 and goes forever to the right, but the purple starts at 16 and goes forever to the left, you're going to have a constant overlap and a common solution. So on that one, we just say our solution is all real numbers. So that's all we have to do right there. All right, let's look at our next one. All right, let's look at this. Finding the height of a race car. To do this, we're going to use tolerance. Now, what mathematical tolerance is defined as it is the margin of error from a goal. So this allows the height or time or whatever to differ from a desired height by no more and no less than a small amount. So, for example, right here, this race car, the race car people want it to have a desirable height of 52. So that is the pre-mode, that is the goal of your race car, is to be 52 inches tall. Now, to be considered race legal, it will be as high as 53, but as low as 51. So really, I'm accepting anything from 51 to 53. So tolerance is what it's allowing you to differ from the goal height. Well, if I want 52, but they'll accept 53 or 51, that's a difference of 1 in each direction. So the formula that we're going to use is h minus the goal. Not really do you have to use h. You can use x, you can use z, you can use m, n, whatever variable you want to use. But the height in this case minus your goal number is less than or equal to your tolerance. So in this case, my goal is that 52, and the tolerance is 1. So I just have to plug into that formula. So h minus 52 is less than or equal to 1. Now, on the next slide we're going to look at, I'm going to show you another formula. So it really doesn't matter. I'm going to show you, you can also use the formula on the next slide to help you with tolerance as well. And we'll look at that after we complete the example. So, but if you just want to remember the tolerance formula, this is the equation you want to remember. H minus your goal is less than or equal to your tolerance. So the absolute value of h minus the goal is less than or equal to tolerance. Okay, last example. They want us to convert the compound inequality to an absolute value inequality. So we have 50 is less than or equal to m is less than or equal to 60. So to do that, we're going to use this formula. The absolute value of m minus the median is less than or equal to the high end minus the low end divided by 2. So first thing we need to do is we need to find out what is the median of 50 and 60. Well, median means middle, so that's 55. Then we have to do high end minus low end. Well, the high end is 60, the low end is 50. So 60 minus 50 is 10. 10 divided by 2 is 5. So now I take these values and I plug them in to create m, the absolute value of m minus 55 is less than or equal to 5. Now, remember if I told you on the last slide, if you only want to remember one formula, it'll be the formula that was on the next slide. And when I was saying that, I was referring to this one, okay? This is the one you want to memorize because this formula will not only work for the absolute value inequality from a compound inequality, it will also work for tolerance. And you're probably thinking, well, how does that work for tolerance? Okay, so the first thing we would do is we would create a compound inequality based on the situation. So I know that the height of the race car can be no less than 51, but it also can be no more than 53. Okay, so to convert this using the formula, we have to say, okay, what is the median of 51 and 53? Well, that median is 52. So then we have to do, okay, what is high end minus low end divided by 2? So 53 minus 51 is 2, divided by 2 is 1. So that's the tolerance formula we got on the last slide. So again, if you just want to remember one formula, this is the formula that works for both scenarios. All right, so that's the end of the lesson. You're going to go work on worksheet 3.2 now. And that's it. Work it, correct it, submit it to your teacher. I hope everybody has a great day. Please remember social distancing, 6 feet apart, wash those hands, wear those masks, and help take care of the neighbor and the people around you. All right, have a great day, and we will see you next time.